Hey everyone, and welcome to our deep dive today. We're heading to the moon for this one.
Oh, cool.
Yeah, to the far side, actually.
This one's mysterious.
It is, we're going to be looking at some brand new discoveries from China's Chang'e 6 mission.
I've heard about this one.
Yeah, pretty groundbreaking stuff.
Yeah, what'd they find?
Well, they brought back samples that might completely change how we think about the moon's history.
Okay. I'm intrigued.
So basically, they found evidence of volcanoes erupting on the far side of the moon.
Really?
Way later than anyone ever thought possible.
Huh. How late are we talking?
Like 2.8 billion years ago. Recent.
Wow.
Yeah, and get this. They even found evidence of volcanic activity going as far back as 4.2 billion years.
That's ancient.
Yeah, like way older than we thought possible.
Okay, so that's definitely going to shake things up a bit in the scientific community.
Big time. Because, the prevailing view was that the far side was pretty geologically quiet.
Right, especially compared to the near side.
Yeah, all those volcanic plains.
Exactly.
But this discovery kind of flips that idea on its head.
Yeah, so much for a quiet far side.
Right, like finding out your quiet neighbor was secretly throwing massive parties for billions of years.
Uh-huh. Good analogy.
And these samples weren't just any old rocks. They found one that was incredibly old. Basalt.
How old?
Like ancient, and it came from a cryptomere.
A what?
A cryptomere.
Cryptomere.
It's basically like a hidden sea of basalt buried beneath the surface.
Wow. So volcanic activity on the moon was even more widespread than we thought.
Seems that way.
Pretty cool.
To figure out how old the basalts were, scientists used radioisotope dating.
The same technique they use for dinosaur fossils.
Exactly. So, we're talking serious ancient history here.
Absolutely.
But here's another really cool thing. They found two distinct types of basalt.
Meaning
they likely came from different parts of the moon's mantle.
Okay, that is fascinating.
So one of the types of basalt they found, this 4.2 billion year old one, came from a source rich in something called creep.
Creep. I've heard that term before, but I'm a little fuzzy on what it is exactly.
It's basically a special blend of elements.
Oh, okay.
Potassium rare earth elements and phosphorus and all these ingredients can really turn up the heat in the lunar mantle.
So creep is like the hot sauce of the moon's interior.
You got it.
I like it.
And what's really interesting is that the older basalt had creep, and the younger one, 2.8 billion years old, didn't. So different parts of the moon's insides were active at different times.
Like the moon was cooking up different batches of basalt over billions of years.
It seems that way.
This is really adding a lot of new layers to this lunar puzzle.
Right. So we've got late-stage volcanoes on the far side, these hidden seas of basalt, and this creep factor influencing things.
A lot to process.
It is. So where does this all fit in with that whole lunar dichotomy thing? You know how the near and far sides of the moon look so different?
Yeah, that's the million-dollar question, right? While these new findings don't completely solve the mystery of the lunar dichotomy, they do challenge our old assumptions about how it formed and evolved.
Okay, so walk me through this. How does this new volcanic activity on the far side change our thinking about the lunar dichotomy?
Well, we used to think that whatever process made the near side covered in those smooth volcanic plains.
The Maria?
Right, and the far side heavily cratered.
Yeah.
We thought that whatever that process was must have totally shut down volcanic activity on the far side, but now we know that's not true.
Yeah, volcanoes were erupting over there much later than we thought.
Exactly. So whatever's behind this dichotomy, it's probably not as simple as we once believed.
So maybe the far side wasn't as geologically dead as we thought.
Maybe not.
Wow. Okay, so then how do scientists determine the age of different parts of the moon's surface anyway?
They use something called the cratering chronology model.
Okay.
It's based on the idea that the older a surface is, the more time it's had to get hit by meteoroids and asteroids.
Leaving craters behind.
Oh, exactly. So the more craters a surface has, the older it is.
Like counting wrinkles on a face to figure out someone's age.
Yeah, something like that.
And what's amazing is that the Chang'e 6 findings actually back up the cratering chronology model, even on the far side.
Really?
Yeah, the age of that 2.8 billion year old basalt lines up pretty well with the estimated age based on the crater count in that area.
That's cool.
So even though the two sides look totally different, it seems like the same basic rules of planetary aging apply to both.
That makes sense.
This is making me wonder, though, what other mysteries are hidden on the moon, especially on that far side.
I don't know, but that's what makes space exploration so exciting, right?
Absolutely. Every mission raises more questions than answers.
It's true, and it pushes us to keep exploring and challenging what we think we know about the universe.
Couldn't agree more.
Yeah.
But hey, before we go full-blown cosmic, let's take a closer look at those two types of basalt and what they tell us about the moon's internal dynamics.
Okay, let's do it.
What makes creep so special? And what does it mean that it was present in the older basalt but not the younger one?
So creep, it's like a geological heat lamp inside the moon.
Okay.
Those elements I mentioned, the potassium and all that, they're radioactive, and when they decay, they release heat.
I see.
So areas with more creep tend to be hotter, more prone to melting, which can lead to
volcanic eruptions?
Exactly.
So that's why that older basalt erupted over 4 billion years ago.
Makes sense, right?
Yeah, because it came from that creep-rich source. But what about that younger basalt?
Good question.
Why didn't it have any creep?
Well, that suggests that the mantle isn't all the same.
Oh, okay.
It's more like a mosaic of different compositions.
Interesting.
Yeah, some areas are richer in creep, while others are creep poor.
So, picture the moon's interior as a giant pizza.
Okay, I'm listening.
With different toppings scattered around.
Okay.
Some slices have extra hot peppers. That's the creep.
I like it.
Making them hotter and more likely to bubble up, while other slices are milder.
So that difference in mantle composition could explain the lunar dichotomy?
Oh, you mean how the near and far sides look so different?
Exactly.
One's all smooth volcanic plains and the other's all cratered highlands.
Right, like two different worlds.
Exactly. But how does the pizza analogy explain that?
Well, some scientists think that the near side might have started off with a higher concentration of creep, which would have made it hotter and more volcanically active early on.
So more eruptions.
Exactly. And that would explain those smooth volcanic plains on the near side.
So the near side was like this hot spot, churning out lava, smoothing everything out.
Yeah. And meanwhile, the far side, with less creep, stayed relatively cool and cratered.
Okay, I get it.
And then we have this late-stage volcanism on the far side.
Right, the 2.8 billion-year-old stuff.
Yeah, which suggests that even though the far side might have started with less creep, there were still pockets of heat and activity that persisted for billions of years.
It's amazing how dynamic the moon is.
It really is.
More complex than we ever imagined.
Definitely makes you wonder what caused all this volcanic activity in the first place.
Right. What was driving those eruptions for billions of years?
Well, one theory is that early in the moon's history, there was a period of intense internal heating.
Oh.
Caused by the decay of radioactive elements.
So like a natural nuclear reactor.
Yeah, kinda. And this would have created a molten layer beneath the surface.
Like a magma ocean.
Exactly.
Wow, that's intense.
And as this magma ocean cooled and solidified, it would release heat, which would create the right conditions for volcanic eruptions.
Okay, so this internal heat engine was driving the early volcanism. But what about those later eruptions, the ones that happened 2.8 billion years ago on the far side?
Right.
What kept things cooking for so long?
Well, there are a few theories.
Like what?
Some scientists think that tidal forces from Earth's gravity might have played a role, squeezing and heating the moon's interior.
So Earth was giving the moon a cosmic massage.
In a way. Yeah, keeping some areas molten and active even billions of years later.
That's wild. It really highlights the connection between Earth and the moon.
It does.
This is all so fascinating. It's like these findings from Chang'e 6 aren't just about rocks and dates. They're making us rethink our whole understanding of how the moon evolved.
You're right.
And what shaped it over billions of years.
We're getting a glimpse behind the curtain, seeing a much more dynamic and complex story than we ever imagined.
I completely agree. And it makes you wonder, what else is out there? What other secrets the moon is hiding?
That's the beauty of science. There's always more to discover.
Absolutely. Hey, before we wrap up, though, I want to hear your thoughts on the bigger picture. Like, what do these discoveries mean for our understanding of the moon's overall evolution?
It really shows us that the moon isn't just some, static, unchanging thing up in the sky. It has its own story.
Yeah, and it's a complex one.
A very complex history.
And this mission just, shows how much we still don't know. It's humbling almost. We think of the moon as this, familiar thing.
Yeah.
Always there.
Right.
But then a mission like Chang'e 6 comes along and shakes things up.
Sure.
Reminds us that there's so much more to explore.
Like those late-stage volcanoes, they raise questions about whether the moon could have supported life in the past.
Really?
Yeah. If there were pockets of heat and liquid water billions of years ago, it's possible that microbes could have survived.
Wow. So now we're talking about ancient lunar life.
It's a possibility.
That's incredible.
It really highlights how studying the moon can help us understand the conditions for life to emerge elsewhere in the universe.
So it's not just about the moon itself.
Nope.
It's about the bigger picture of life in the cosmos.
Exactly.
Mind-blowing.
And I think these findings are going to have a big impact on the scientific community.
Yeah, I can imagine.
It'll definitely inspire new research and new questions about the moon.
Absolutely. So, to wrap things up,
Yeah.
we've learned that the moon is much more dynamic and complex than we thought.
Definitely.
Volcanic activity lasted way longer, and the distribution of creep might explain why the two sides look so different.
It might.
And maybe even more importantly, we're now thinking about the moon's potential for past life.
It's a big question.
Huge. And it's all thanks to missions like Chang'e 6.
Yeah, it's really pushing the boundaries of what we know.
It's like the moon is revealing its secrets to us, little by little.
And there are probably many more secrets waiting to be uncovered.
That's what makes space exploration so amazing.
It's all about the pursuit of knowledge, you know?
Exactly. The drive to uncover those secrets of the universe.
I couldn't agree more.
Well, this has been an incredible deep dive. Thanks for joining us.
My pleasure.
And remember, next time you look up at the moon, think about those hidden volcanoes, those ancient seas of basalt, and the possibility that life might have once existed up there.
It's pretty amazing.
Keep exploring, everyone.